For most of the 20th century, cosmologists believed the expansion of the universe was slowing down. It seemed obvious. After the Big Bang, space expanded rapidly, but gravity, the ever-present force pulling matter inward, was always at work. Galaxies, clusters, clouds of gas, every speck of mass tugged on every other. The larger the structure, the stronger the pull. So the natural expectation was this: the universe would keep expanding, yes, but more slowly over time. Gravity, like a cosmic brake, would gradually slow the motion. But then came the shock. In the late 1990s, two separate teams of astronomers set out to measure how the expansion of the universe was changing over time. They studied distant supernovae, exploding stars in faraway galaxies. These weren't just any stars. They were Type Ia supernovae, cosmic standard candles. Their brightness is so consistent that, by comparing how bright they appear to how bright they should be, scientists can calculate distance with astonishing precision. And by measuring how much their light had been stretched, or redshifted, researchers could also estimate how fast the universe was expanding when that light left its source. When they plotted the results, the surprise was immediate. The supernovae were dimmer than expected, not because they were less powerful, but because they were farther away than any decelerating model predicted. In other words, the expansion of the universe wasn't slowing down. It was speeding up. A moment that redefined modern cosmology. This discovery, published in 1998, earned the 2011 Nobel Prize in Physics. And it raised a profound question. What is driving this acceleration? Enter a new concept, or rather, the resurrection of an old one. Dark energy. A mysterious form of energy that doesn't clump, doesn't dilute with space, and exerts a negative pressure. A kind of gravitational repulsion that pushes everything apart. It had first appeared in Einstein's equations as the cosmological constant, a fudge factor he added to keep the universe static before we knew it was expanding. Einstein later called it his biggest blunder. But now it was back, not as a mistake, but as a crucial clue. Dark energy, whatever it is, seems to make up about 68% of the total energy content of the universe. It's not just part of the story, it dominates it. Its effects are subtle, but cumulative. Over vast distances and cosmic timescales, it reshapes the fate of everything. Galaxies that are already far away will become unreachable. The observable universe will shrink, not in size, but in content, as light from more and more galaxies fails to reach us. The night sky will grow lonelier, and one day, if dark energy remains constant, the universe will become a vast, cold, empty void, expanding forever into silence. Some theories propose even stranger endings, where dark energy increases over time, tearing apart galaxies, stars, planets, even atoms, in a final event called the Big Rip. We don't know which path reality will take, because, for all its importance, we still don't know what dark energy is. It doesn't behave like anything else in physics. It doesn't radiate, interact, or form structure. It's everywhere, and yet completely invisible. But it's not nothing. It has energy. It shapes space-time, and it challenges the very foundations of our theories. What began as a small deviation in a few supernova measurements has become a central mystery of modern science. And it all started with a simple question: how fast is the universe expanding? Sometimes the most ordinary questions lead to the most extraordinary revelations. The cosmos, it seems, is not only expanding, but rushing away from us, propelled by a force we do not understand. That is both terrifying and beautiful, because it reminds us that the universe is still writing its story, and we are still here, reading the latest chapter.